Hello AP Calculus, this is Mr. Fugay. In this next video we are going to continue our conversation about different techniques of integration, more specifically involving fractional integrands and using rational functions. So for this video we're going to focus around inverse trig, and we're going to indirectly talk about inverse trig through the acknowledgement of remembering our inverse trig derivatives. Now the ones that I'm going to have you in particular focus on for this video is the derivative for arcsine and the derivative for arctangent. Now, why are we focusing on these two and not the other four? Here's my quick explanation. We will not be looking at antiderivatives that look in this form here with the absolute value of x and square root of x squared minus 1. So inverse secant, inverse cosecant, those are going to be types of problems we're not going to encounter. Why then am I taking out cosine and cotangent? Well, cosine, as you remember, its derivative differs from inverse sine by just a negative sign. And so as we'll see in the video, if there was ever a negative in the problem, you simply could just factor it out outside of the integral and leave your answer as inverse sine. But that does bring up an interesting point in that there is a distinct relationship between these two functions and as well as the inverse tangent and inverse cotangent functions. So as we move on, we're going to take a look at a few examples here. And so here's our first example. So when looking at this, in the previous videos we've talked about u substitution as a technique. We've also looked at using partial fraction decomposition. But in this particular problem, x squared minus 6x plus 10 is not going to factor. So in order for us to do this, we are going to have to utilize a concept from algebra called completing the square. Now, if you need a rehash on completing the square and how it works, please check out a link below this YouTube video, as well as on the Canvas page if you need to refresh what completing the square exactly is. But what we're going to take a look at right now is we're going to look at this expression, and my job is I want to try to use completing the square to rewrite this as inverse tangent's derivative. So if I can write it in the form 1 over 1 plus something squared, we now know that its antiderivative would be arctangent of that something. So let's go ahead and go through that example. So let's first go ahead and let's take care of the completing the square process. So when we do that, we're going to look at the expression x squared minus 6x plus 10. And so there's a couple different ways to do this. There's actually you could take this 10 and break it down, but I'm going to show you the more generic way that we could go about this, okay? So I'm going to break it down and I'm going to ask myself, what number needs to go here so that the x squared minus 6x plus missing term expression will factor into a binomial squared? And what we know from completing the square is that we're always going to take the b value, cut it in half, and square it. So half of negative 6 is negative 3, and negative 3 squared is 9. Now we can't just add a 9 to an equation or to an expression without offsetting it. And so I'm going to offset that by subtracting the 9 here. That's going to allow me to simplify this expression to be x minus 3 quantity squared plus 1. And this is what I'm now going to substitute back into my integral expression. And so that's what we're going to go to right now. So we have now the new integral is going to be 1 over x minus 3 squared plus 1 dx. Now this has now allowed us to turn it into a form that looks very similar to the derivative of arctangent. So what we're going to do here, and some of you may notice this and say, well, I don't need to use u substitution, and that is true because the u term that I'm going to use here just has a derivative of 1, but just for consistency, I'm going to go ahead and do a u substitution to show you where this comes from. So I'm going to make u equal to x minus 3, therefore du will be equal to dx. When I substitute this back into my integral, I'm going to get 1 over, and then I'm going to leave that blank, and I'm going to insert u in its place here. I'm going to insert du in its place here. And as you can see, I now have the integral of 1 over 1 plus something squared. We know that that antiderivative will then be inverse tangent of that same u value plus c. Of course, for our last step, whenever we do a u substitution, we're going to want to substitute that back in so that our answer is in terms of x. So we're going to call that x minus 3 plus c, and we have our first antiderivative in this practice set. What I'd like you guys to do at this point is take a look at this example here, and I'd like you to try this one on your own. Pause the video, and when you've completed, we'll have an answer for you. Okay, welcome back. Here is the solution for the practice problem I asked you to do. As you can see, very similar process in where we're going to take that bottom term, complete the square, to turn it into a form that resembles arctangent's derivative. And that's where we come up with our final solution of arctan of x plus 5 plus c. So moving on to our second example in this video, we're going to have a total of 3 examples we're going to do together on this video. This next one's going to be a little bit more algebra intensive in where we're going to have to work with square roots. Our goal here when we have 1 over the square root of something is we are going to want to try to rewrite it so that it can resemble inverse sine. And so that's what we're going to begin with this process. So same thing as we've been doing in the last example is I'm going to take this term right here, and my goal is to use completing the square to rewrite this. So let's go ahead and do that over here on the left-hand side. Now this one's going to be a little bit more algebra intensive because the a term is 2. And as you may recall from completing the square, we must factor out that negative 2 because the a term must always be 1. So that's going to make this plus 4x plus, I'm going to leave a blank here, and I'm going to leave that minus 6 on the outside. We're going to let that kind of stand alone. So what we're going to do now is we need to determine what the new c value is going to be. It's half of 4, which is 2, and 2 squared is going to be 4. Now, prior to doing this, we need to be very, very careful with this. In order to do this problem properly, I cannot add a 4 here. Why? Because this really isn't a 4. This is actually negative 2 times 4 because this negative 2 that's on the outside would have had to been distributed to it. So really what I added to this equation in disguise was a negative 8. So in order to offset subtracting an 8, which is what essentially is happening here, I'm going to add an 8 on the outside of this parentheses. That's a really important thing whenever you complete the square and you have a factored GCF on the outside here that you need to consider. So with that being said, let's go ahead and let's rewrite this, because we can now take this and call this x plus 2 quantity squared plus 2. And that's what I'm going to rewrite my integral to say. So let's go ahead and let's write this out. So we're going to have 1 over the square root of negative 2 x plus 2 quantity squared plus 2. Now we're not exactly ready to process this yet, because in order to make this the antiderivative of inverse sine, we need to make it say 1 minus something squared, and right now I have 2 minus 2 times something squared. So in order for me to get this prepared to take the integral of, we're actually going to go ahead and do some algebra work down into this denominator. I'm going to start by factoring out this 2, and what that's going to leave me now with is, and I'm going to reverse these by the way, so I'm going to call this now 1 plus, or sorry, I take that back, 1 minus parentheses x plus 2 quantity square. Okay. Why is that helpful is that I can now separate these two things. I can separate this out and put this as a constant out in front of the integral. This is the same thing as 1 over the square root of 2 when I pull that out. So what my new integral is going to look like now is, let's put another equal sign there, 1 over the square root of 2, and now it's going to be the integral of 1 over the square root of 1 minus x plus 2 squared. What you may recognize here is that this is going to look like the derivative of inverse sine, keeping in mind on the side, and we don't really need to use the u substitution here, but just for the record, if you wanted to, we could call it that, substitute it out, but this is going to be what's inside of the arcsine term. So my antiderivative, leaving that 1 over square root of 2 there, is going to be inverse sine of x plus 2 plus c. And that's going to be my final solution for this question. As we've done with the first example, I'd like you to try another problem similar to this. Here is the next one I'm going to have you try. Just to be careful, there is a little bit more algebra to go on in this problem, but please try it out first, and then I will go over the solution with you in just a second. Alrighty, well, welcome back. This is the solution to the question, and we do have a little bit of conversation I'm going to have with you here. Just so you know, the final answer should look like this: arc sine of 1 over root 2x plus 1 over root 2, which also could technically be called x plus 1 over root 2 as an alternative. But let's talk a little bit about what's going on here, beginning with the completing the square process. So just like we did, I showed you in the previous problem, I'd have to factor out that negative right here. So this is really not a plus 1, but actually a minus 1, hence why I'm adding 1 again over here, or what it appears looks like I'm adding 1. So this is going to be my new denominator term, and here's where I rewritten it. Now, the difference here is in the last problem I did, there was a 2 right here, so it made it really nice and simple to factor it out like I showed you before. However, when I do it this time and I pull the 2 out, this does become 1, but now this becomes a half, and this 1/2 becomes an issue that we now need to discuss. In order for this to be the correct form for arc sine, this needs to be 1 minus something quantity squared. Well, the 1/2 is not part of the square. So I'm going to show you right now with this green arrow how I went about to making this a singular term quantity squared. So that's down here in green. Oh, just as a reminder here, 1/2 can be written as something squared because I can call it the square root of 1/2 squared, which then simplifies to 1 over the square root of 2, all of this being squared. The other algebraic property to remind yourself here is that if I have two terms that are both being squared, like 5 squared times 2 squared, is I can call that 5 times 2 quantity squared. Taking a look down here in the bottom, this is what I did in order to make this work. So I rewrote the 1/2 as 1 over square root of 2, quantity squared, and then to multiply them together, and then I distributed that 1 over square root of 2 to the problem. And that's where my substitution here in green comes into play. From here, I did do a u substitution, so I called this 1 over root 2x plus 1 over root 2. I went through the remaining process here to get dx by itself. I substitute that back in. That means that the root 2 and then that 1 over root 2 that I factored out in the very beginning of the problem are going to cancel each other out. I'm now ready to write this as arc sine, and so I go ahead and I complete that, and there is my final answer. So for the last question in this video, what we're going to take a look at is one more example where it might look like that we need to actually use an arc sine form, but we're actually not going to, and I'll explain why. So in this integral here, it looks very similar to the very first problem that I did with you. However, when we do the completing the squares, I'm just going to do kind of quickly here. We have negative x squared minus 4x plus 5. We're going to go ahead and do the same thing that we talked about on the last question. So let me just write that out for you here. The number that we need to use here is a 4. However, that's really a minus 4 because of this negative sign in front. So I add a 4 here. And so when I do that, I'm going to get, and I'm going to conveniently write it, actually, I'm going to leave it this way for now. It's going to be x plus 2 quantity squared plus 9. And so when I write my integral over here, I'm going to have 1 over negative x plus 2 squared plus 9 dx. Well, the problem with this is that there's really going to be no way for me to make this arctangent. This is actually going to end up being a u substitution problem that's actually going to involve partial fraction decomposition, which is a little bit of a review from our previous lesson. So when I do this, I'm actually going to be able to write it in this form, negative u squared plus 9. And as you may be able to recognize here, that's actually going to be a difference of squares. So I can write this as 3, I'm going to flip the order, 3 plus u, 3 minus u. And what we can do here with this problem now is complete this using partial fraction decomposition. And that's exactly what I'm going to have you do at this point in the problem. So pause this, and as a review from the last lesson, go ahead and complete this integral using partial fraction decomposition. Welcome back, and here is the remaining work for the problem. So at the top here you can see my breakdown of the partial fraction decomposition, and we solved this to find the values of capital A and capital B, and you can see that I plugged that in over here on the left hand side. A really important thing that I want you to keep in mind as we wrap up this problem is that this was a minus u, a negative term, and so technically another, I guess, embedded u substitution has to be considered here, because when you eventually take the derivative of 3 minus u, natural log that is, it becomes 1 over 3 minus u times the derivative of the inside. Hence why we have to have this negative sign in front. That was probably the most common mistake that I would expect you to make in doing this problem on your own, but as you can see, I use the properties of logs to simplify my problems. So that will conclude this video on completing the square among other rational expressions. Thanks for watching.